All right, welcome class. Today we're going to kick off our next project, which is building rockets. So here in a couple weeks we will be launching rockets outside, probably out in the soccer field. But again, this is the project kickoff. So before we get started, I know some of y'all have already caught on to this, but some of y'all might not be aware. But all of my ed puzzles are open and unlocked for you to take as many times as you need to get the score that you want. So if you're trying to get a or 100% and you need to take this ed puzzle 2-3 times, have at it. So without further ado, let's get started. So the concepts we're going to be talking about along with our project are tolerances and reverse engineering. So project overview. So I've got some rocket kits. They've been on the shelf for a little while. We're going to use a few of the parts from each of the rocket kits, and we're going to reverse engineer the rest, the plastic components. You're going to make your own modifications to those designs to try to improve upon the overall flight of your rocket. So, for example, the body tube of the rocket will be from the kit, but you will design your own nose cone. Essentially, any of the parts that are near the engine have a potential to, explode if they're made out of the wrong parts. We're going to use the kit parts so that way we don't have any of those safety issues. But the things that are plastic or wood and are a little bit further away, we're going to design those in Onshape and potentially 3D print some of those. With that, you need to ensure that whatever you do make fits into the rocket, the kit rocket, without falling out in flight. That obviously, if your nose cone falls out, you're going to lose your aerodynamics and you're not going to hit full height. So that would not be good. So concept there is called tolerances. So kind of start out with a little bit of a problem here or food for thought. If your rocket has a body tube and the inner diameter of that is 2 inches, how big can that nose cone be to fit and still not fall out? So you think if you got your pipe like this, has a hole, nose cone goes inside, it needs to be snug enough to fit in, not just fall out, but not be too big to where it can't go in, or when what's called the escape charge ignites, it doesn't. The nose cone doesn't eject. It's not too snug. So, with that in mind, you have to take into account what's called a tolerance. So, again, imagine you've got that 2-inch cone or 2-inch body tube, and you have a nose cone that has a diameter here of 3 inches. It's not going to fit. It's just too big. What if it was, say, 1.95 inches versus that 2-inch body tube? It probably would slide in. Might be a little snug. It would probably just catch just enough so it wouldn't fall out too easily. But when that escape charge hit, it would pop out. And what about if it was only 1.5 inches? Probably wouldn't fit too well. It probably would slide right in. It would probably go right through, land on the engine, and probably explode or cause some other sort of issue. I kind of made a CAD of these real quickly, so I'm going to flip over to that screen, kind of show you exactly what I'm talking about here. 1 second. So here we go. We've got the overall 3-inch. Show you the dimensions. So we got our 3-inch diameter nose cone. In this one we got our 1.95 inch diameter nose cone. And last but not least, the 0.1 or the 1.5 inch. So kind of small, medium, and large. So again, got the same 2-inch diameter body cone. If we try to put the 3-inch in, as you can see, it's too big. It overlaps and kind of sticks out on all the ends. Doesn't really fit into that hole too well. On the other end, if you've got the 1.95, kind of fits right in, doesn't fall out too easily, doesn't slide all the way through. It probably would, have some friction there and stay in place. Whereas if you make it too small, it clearly just does not sit in there, just slides right through. And if you had, engine and fire down here, this would go straight down to the engine and fire, and you would just have all sorts of issues. So, all right, so let's see. Back to this. So concepts within tolerances. So there's two typical types of tolerances. One's called a unilateral, and the other one's called a bilateral. So if you notice, the only difference in the two is the prefix at the front. One is uni, which means one, whereas bilateral means both or two. So a unilateral tolerance means the variation is only allowed on one side. Either can be bigger or smaller compared to the stated dimension. So here in the picture, this has a gap of 36, we'll call it millimeters. If you were trying to create a clip or something that goes in this space, it could be 36 millimeters. Cannot be bigger, but it can be smaller by 0.3 millimeters and still not have a issue once you assemble it. Here on the bottom one, 25 millimeters can be a little bit bigger, plus 0.1, plus 0.1, but it can't be smaller. There's no minus sign, so the small side is 0. The other type is called a bilateral tolerance, which again means it can be on both sides of the stated number. So it can be bigger and smaller versus that stated. These come in two kind of flavors. You've got ones that are kind of equal. So you'll see 36 with the plus minus sign, 0.2. That means it could be 36.2 all the way down to 35.8. So add 0.2 to this is the max, or subtract 0.2 from that to get the minimum. So if you built a clip or a nut or whatever goes in this space that's somewhere in that dimension, you'll still be able to assemble and not have any sort of problems or issues. Your other flavor of a bilateral tolerance is when it's not the same number. So in this case, 36 plus 0.1 all the way down to 36 minus 0.2. So you could have 36.1 all the way down to 35.8. You'd still be within tolerance. Your part would still work. You'll also sometimes see those with angles, and so there's some examples there. We won't get into too much of with angles, but again, when you're building and you get out into the industry, you might see that. So again, it's the same thing, same concept. Along with that, so tolerance overall is just the range of variation of measurements allowed before a part becomes defective. The upper end is called the upper deviation. It's the maximum that's allowed for that dimension, and it still be successful, still fits, doesn't fall out. Lower deviation, again, minimum variance, the dimension can be below the stated dimension, and the assembly still be successful. Example, our body tube, the nose cone won't fall out if it is still within the tolerance or within that lower deviation bound. All right, so back to our project. So this is our overall rocket. This is what we're going to be building. The kits do not come painted, so that will be something that we do in class. Here's kind of the list of parts. So I kind of broke it out into the plastic pieces or the wood pieces that I know we can 3D print and replace, modify as you see fit, and the ones that are not. So the body tube, which is this long tube here. The engine block is typically a ring like this. It's what blocks the engine from all of the recovery stuff at the top. Spacer, this is what holds your engine to some extent. On the bottom, make sure that it doesn't go too far up. Also make sure that that engine block is far enough up into the body tube. Streamer, that's the red thing, so it's going to go pretty high up. You might lose visibility of something small, so having a bright, colorful streamer makes it easier to see. The launch lug is a metal piece that kind of holds the engine in place so it doesn't fall out, start a fire on the ground. Shock cord goes between your nose cord and the body tube as your engine depletes its normal energy after a few seconds and it kind of stops and hits its peak height. It'll have an escape charge, an escape charge. At that point, the nose cone pops out, the streamer comes out, but you still need to have everything that connects. So that's the shock cord. So again, all of these are the parts that we're not going to 3D print or recreate because they're either too close to the engine and potential fire, or things that aren't 3D printable, cords, streamers, stuff like that. Then you got your nose cone, so basically the tip. You can go online, you can see there's a whole bunch of different kind of nose cone ideas and designs, so you don't necessarily have to go with this very pointed slender. Granted, it's very aerodynamic, so again, that's kind of part of this project. The nose cone insert, so that's this little white piece right here. That goes into the bottom of the nose cone and then has the shock cord connect to it. It's basically a hook. You could probably 3D print and design one where that insert is already built into the nose cone and don't have to worry about it. And then the fins. So in this case, these kits come with balsa wood, pretty lightweight wood. You can also 3D print if you wanted to do a little bit different shape design, maybe some engraving on it, just to give your rocket ship a little more flavor. So how this project's going to work. So breaking it down into the phases are kind of the assignments. And you can see, again, as is with everything else, we're following that engineering design process. So phase 1, we're doing our research. In your Google Classroom, there is a Google form. So just like the BattleBots, there's going to be a little bit of a research part of this project. And that'll be due this Friday. So Friday, February 21st. It has basically these parts here listed out. And it's going to ask you what is the purpose of it, things like that. So, what happens if you modify it? Is it modifiable? No, yes, no, those kinds of things. So the things you should be thinking about as you're starting to build, working on your own design. Next, phase 2 is the reverse engineering piece. So not going to have you make a hand sketch this time. You can. It's absolutely recommended. It makes it easier to do the CAD. But from a grade standpoint, you're going to create a 3D model in CAD, so in Onshape, of each of the components with accurate dimensions. So each of you will get a kit. We'll do this in groups no more than 2 or 3, depending on the bell. Each component must be its own Part Studio tab. So the fin has to be in a different Part Studio tab than the tube. Same with the nose cone, etc. So you will end up with quite a few Part Studio tabs. That way you have separate parts that could later be assembled if we wanted to go into an assembly mode. That's just the right practice for an engineer. So in Onshape, you're going to go into classes. It's in the left-hand menu. You're going to go down to your bell, you should only have your bell listed. Click on that, find the assignment that says rocket ship, and you're going to start that assignment. That will open up your workspace. You can then go about sharing it with your group members, and it will automatically already be shared with me. I can see who contributes what in the history of your project, so make sure that each of you are doing something in Onshape, and it's kind of evenly weighted, so that way it makes it easier to grade. If you have somebody that's an anchor and isn't helping the team, it makes it very easy and obvious on who should get the grade and who shouldn't. So don't be an anchor. If you're a carry, make sure you're trying to divide that work up and not just do all the work and kind of bogarting it. Share the work so everybody learns something. Once you're done, you need to do 2 things. Hit Submit Assignment in Onshape. It should be at the very top. That lets me know in Onshape that it's done and ready for graded. But you also need to go into Google Classroom and press submit as well. You don't have to take any pictures, make any slides in Google Classroom. Just press submit. That triggers me to go to Onshape to view your Part Studio tabs, your file, your document there. So again, submit in Onshape, press submit in Google Classroom. All that's going to be due by Friday, February 28th. If you divide and conquer this, the 3 to 4 bells you'll have at a minimum, more than enough time. Should be no reasons why you can't get this done. On to probably the more fun part that everyone's looking forward to is the physical build. So that's where we're going to build, paint, etc. your personal rocket design. If you need something 3D printed, you need to tell me. You need to tell me what color, how many, etc. If it seems reasonable, I will do it. You can see what color filament I have. Just go and observe. Do not open, but just go and look at the top of each of the 3D printers, and you can see what filament is available. If you're asking me to 3D print 95 fins, that doesn't make sense to me. I'm not going to do it. I'll print the 3 that matches your kit. If for some reason your design, say, has 4 or some different number that's reasonable, we can have a conversation. You can show me your design, and we can go from there. This part, there will probably be a delay between doing phase 2 and phase 3. We've got our web exam coming up. But I will make sure you have at least 3 classes to complete this before launch day. The standard kit says it takes 1 hour to build, paint, and do everything. Your class period is 47 minutes, so it should not take you more than 2 classes. I know some of you all are not as quick or expedient. You may not have done this, so giving you 3 classes gives you more than enough time. Don't lollygag, don't screw around and waste time. We'll have a launch day. You've got to be ready to launch. I'm going to have to make sure that it's a decent weather day. It's not raining. It's not too overcast. If it's too cloudy and you can't see where the rocket goes, it kind of defeats some of the excitement of seeing that rocket go up. So again, be ready on launch day. Otherwise, you'll be disappointed when your rocket never gets launched. And overall, that's the project. So again, if your Edpuzzle grade on this isn't the best, feel free to rewatch and take again to get the best grade you can. Otherwise, if you have questions, if things weren't clear, come talk to me, send me a note, whatever works for you. And we'll see you all in class. Thanks all.